Here we go with semester 2, computational analytical methods. So what we're doing now is to work towards you taking the examination to our exam at the end of semester 2. Okay, so we're a fair bit of additional integration methods and through other techniques as well that we're going to go through over the period of the next 12 teaching weeks. We got 2 weeks up until, got 2 weeks teaching, then half term, then we got Easter, and then time Easter's up, we'll be nearly finished, hopefully. Alright, so further integration methods. Functions that require integrating, okay, don't always have, not always in one of the standard forms in our table, standard integrals. So you should all have one of these. Today we're on the page of that, and we're thinking about integrals. So that's shown below. However, it's possible to use some further techniques to change the function into a suitable form that can be used to integrate using further methods. What we're going to consider is 3 different things. Integration by algebraic substitution. We've already had a little go at that, because if you had a function, sine or cosine function in your assignment that had some reason I ain't got a set of notes for you, Dan, so I don't know why. I'll sort that. But already had a go at algebraic substitution, because if you had a function in your assignment with a phase shift, then you needed to use algebraic substitution. However, if you didn't have a phase shift, you didn't need to do it. You could have just integrated directly. The only one I had a look at so far, someone didn't have a phase shift, but they still used algebraic substitution. No, I'm not marked any yet, so I just had a quick look at that one. Alright. We're also going to integrate by partial fractions. So next week I'm going to revise partial fraction methods so that we know how to resolve a function into partial fractions. And there's a need for those skills in electrical principles next year as well, so they'll come in useful. And so if you think you can forget all this maths between now and next year, the answer to that is no. Andrew and Jasmine are going to find that out this year, because they're doing the electrical principles this year as well. Okay. We're also going to do what's called integration by parts. So 3 further methods of integration that allow us to integrate more complex functions. Okay. So if we look at this function, we talk about determine the integral of the cosine of 3x plus 7 dx. So to start with, we deal with a function, deal with finding an indefinite integral. An indefinite integral. Okay, but we haven't got any entries in the table that look like cosine of a function of x. Okay, so we're going to use the method of algebraic substitution. So we can solve this using our algebraic substitution. The method is that we let u equal 3x plus 7. We then differentiate that. So we say, therefore, du by dx is equal to. How do we differentiate 3x? It becomes 3. Yeah? That comes from the fact that we can write that as 3x to the 1. Yeah? And we bring the 1 down, so we say, so dy by dx is equal to 1 times 3 times x to the 1 minus 1 x to the 0. Any number to the power of 0 is 1. So that's effectively 1 times 3 times 1. Yeah, so that just the x term disappears. Alright? And then we rearrange that, this differential, so that it is in terms of dx. So we need to make this dx equal something. So therefore, dx is equal to du by 3. What we can then do is put that, replace, right, sorry about that interruption. So what we can now do is write that the integral of cos 3x plus 7 dx is equal to the integral of cos u times du over 3. Now, in our table, we've got function cosine, yeah. So we can now integrate. What happens with this 3 as a constant? So we could write that as a third du. What happens to constants? No, not when you integrate. What can we do with constants in integrals? Yeah, so we can say it is a third integral cos u du. So that bit, this bit here, would show that we could have that integral in terms of u instead of x. Yeah, by replacing dx with du by 3, we then got it in terms of u, which is what our variable is at the moment. Yeah. So now how do we integrate cos u? In the table, what's the integral of the cosine? Yeah, and in this case, a is equal to 1. Yeah, so you don't. So as a third, cosine is 1 over a sine, a third sine u, plus what we always got to have in definite integrals, plus a c on the end. Yeah. So and then we just replace the u with what we call u in the first place. Yeah. So, look at example 2. If we look at that one, we've got 2x minus 5 in brackets, and the whole bracketed term is raised to the power 7. Now, you could, if that was raised to the power 2, you could just multiply out the brackets and integrate separately in the normal way. But when that's to the power 7, you're going to multiply out 7 sets of brackets. You're going to end up with a really complex function. It's going to take a long while to integrate properly. So in this case, we could use substitution. So how do I start? Let u equal 2x minus 5. Yeah. That's what we're going to do. Du of dx is equal to, differentiate 2x, we get 2. Differentiate minus 5 disappears. Yeah. Dx is equal to u over 2. Now we do our substitution. So we can say that the integral of 2x minus 5 all to the 7 dx is equal to the integral of u to the 7 du by 2. I've written u in place of 2x minus 5 in brackets, and I've written du by d2 in place of dx. Yeah, we can equal a half integral of u to the 7 du equal to half times, how do we integrate u to the 7? It's the ax to the n one. So we say it is u to the 8 over 8, yep. What's missing? Plus c. When you've integrated, du disappears. Yeah. So when you go from the integral, well, you're taking the integral of that. When you integrate it, that symbol and the du just goes. Because you've done your integration. Yep. And how better can we write that? If you think of it as it is half times an 8th times u to the 8 plus c. Half times an 8th is what we've got to do now. Replace u, haven't I? 16th. What did we call u? 2x plus, not 2x minus 5. So a 16th brackets 2x minus 5 to the 8 plus c is the integral of that function. Yep. Right, all happy with that? Yeah? So, third example. Find the integral of 4 over 5x minus 3 brackets times dx. Right, help me, where do I start with this one? Yeah, write it out, let u equal 5x minus 3, and then what? Here. What do I do with that? Yeah, differentiate it. Equals 5. And then we rearrange for dx. Yeah, we need to dx is equal to u by 5. Yeah. Therefore, the integral of 4 over 5x minus 3 dx can be written out as equal to the integral of 4 over u du over 5. Yep. Where can I go from there? What constants have we got? We got not quite 5. We've got a 5. That's 1 over 5. Yeah. Anything else? And 4. Yeah. That could be written as 4 times 1 over the u. So we can bring the 4 out, and that's a 5th times du. So we can bring the 5 out. The integral of 1 over u du. Is there anything in your table of integrals that is 1 over x something? 1 over x. Lim. Yeah. Natural logarithm. So we can say that is equal to 4/5 ln u plus c. Don't forget our constant of integration. And then we replace u with what we called u in the first place. 4 over 5 ln brackets x minus 3 plus c. We need all of that laid out like that for full marks in the exam question. Yep. Right. Happy with that? Yeah? So, of course, we can also evaluate definite integrals that are a function of a function, effectively. So we're looking at here at evaluating the integral between 1 and 0 of 2 times e to the 6x minus 1. So the index of a exponential function is another function of x. So e to the power of is a function, and then e to the power is also a function. The 3 significant figures. So, my suggestion here would be that you integrate the function and then apply the limits afterwards. Yeah. So, where would we start with integrating that function 2e to the 6x minus 1? let u equals 6x minus 1. Yep. Differentiate. Du by dx is equal to 6. Therefore, dx is equal to du over 6. So we can say the integral between 1 and 0 of 2e to the 6x minus 1 is equal to the integral between 0 and 1. Hang on, let's take them limits off there for a minute. Don't complicate things with them for a minute. Integral of 2e to the power of u du by 6. Sorry? I've replaced the x. Oh, here. Yeah. Okay. What constants we got here? Yeah, 1 over 6 and 2, so it becomes 2 over 6. Well, how better could we write 2 over 6? 1/3 integral of e to the u du. Yeah. When we integrate e to the u, we get remember, in this case, comparing what you've got with this table, u is x, not a. There's no number in front of u there. Yeah. So the integral of e to the u is just e to the u. Yeah. So that's equal to 1/3 e to the power of u plus c. That's integrated it. And now we put 1/3 e to the power of, what did we call u in the first place? 6x minus 1. Yeah. And now now we need to say that's 1/3 times e to the 6x minus 1 between the limits of 0 and 1. Can you remember how we do definite integrals? It's going to be 1/3 times all of it. So you want some big brackets. And then take away the value when it's 0. So you take the top limit. So we say that's the value of e to the power of 6 times 1 minus 1. We replaced x with 1. Yeah. Close the brackets. Take away the value of the function 6 placing 0 minus 1. Close that set of brackets. Yeah. Alright. So that's going to be a third times e to the power of 5 minus e to the power of minus 1. Yeah, everyone agree? If you plug that in your calculator, what do you get the 4 significant figures? $49.35 to 4 significant figures. Yep. Remember, once we want to evaluate a definite integral, we can forget the constant of integration, because if we add it in, they cancel each other out anyway. We end up with c and minus c, and that cancels. So we just ignore them once we get to the stage of evaluating a definite integral. Right? All happy with that? Right. In your notes, you've got on the final page, beginning with question 1 being 2 sine of brackets 4x plus 9, you've got some examples where you need to use algebraic substitution to have a go at with the answers in good old-fashioned John Bird form. So rest of the session, have a go at them, get this method down by pat so you know what you're doing, you know what you need to do. Yeah, I can, Daniel, sorry.